So this is the weekly training video for the physics peer tutors at the James Madison University Science Math Learning Center. The difference with this video is I might share it with some people who are not in our peer tutoring program, who are not even at James Madison University. And the reason for that is something you'll see in just a moment. So to begin with, of course, we're doing our tutor training all semester remotely because we're trying to stay safe in this time of COVID. I'm hoping to see my tutors again soon at the learning centers when we go back to this hybrid model and in person. But today's training is going to be tied in nicely with this question. If individual forces can be said to act on an object, just take that as a given even if you don't like the language, what does the net force act on? Take a moment to tell me what you think is the best answer of these. If you need to pause the video, that's fine, but I don't want you to overthink it. I kind of want your gut reaction because I think that's how most of us who follow Professor Brian W. Frank on Twitter responded when we responded to the poll. Professor Frank, by the way, teaches at Middle Tennessee State University, I believe. I think this question's fantastic and it fits really well with what I'd like to talk about with my tutors this week, which is vectors. So let's point out first that I know that you, the peer tutors, understand what vectors are. In an introductory physics course, vectors are usually presented first in one dimension. And by presenting them first in one dimension, they're not usually very difficult, which means that sometimes students don't understand why they are needed. In fact, they are sometimes seen as overcomplicating a really simple question. This professor, for example, moves 2 meters to the right. If she then moves another half meter to the right, how far is she from where she started is a really simple question. I can't complicate it much in one dimension. She moves 2 meters to the right and then 1 meter to the left. How far is she from where she started? What is the total distance she traveled? Students don't want this concept of a vector in order to answer this question because in one dimension it is pretty straightforward, no pun intended, and it's not that difficult. It gets a little bit more complicated when you start talking more about what that negative vector means and how arbitrary it is for us to define a direction that's positive and negative. That becomes a bigger issue in the lab courses usually than in the lecture courses because we typically take a question like this one on the screen or on a piece of paper and just say to the right is positive x and to the left is therefore negative x. And it's a much more interesting conversation to have two students facing each other across a lab track and try to figure out which way is positive on the track. Again, in one dimension, not that difficult. The one place where I think it is most useful in one dimension is something that actually doesn't usually get talked about very much, which is relative motion. So if you get into questions like this one where the train is moving to the right at 15 meters per second and the person on the train is walking at 1.2 meters per second relative to the train, the idea of whether those add together or subtract from one another, including things like two boats are in the same river but they're traveling in opposite directions and what's the relative velocity of one to the other, that whole thing, that whole type of question can get really confusing really quickly if you're doing it just by reading. And by taking the moment to write down the actual vector arrows and show them pointing left or right, students usually are able to piece this together as a much simpler problem than the initial wording without any visuals might imply. Another thing that we could do in one dimension that, again, I don't think enough time is usually spent on with students is talking about how delta V and V initial relate to one another in one dimension. If they're both positive versus if they're both negative versus if they are opposite signs of each other. This can be really helpful because we know that students typically have some issue with the idea of a negative acceleration. OpenStax stops and gives us these specific images and devotes a little bit of space in their book to trying to address what all instructors and tutors know is a recurring issue with students, and that is that the term negative acceleration sounds a lot like decelerating, and saying it as acceleration in a negative direction can somewhat help, but spending some time going through problems with it, showing that acceleration is a function of delta v, and delta v is either pointed in the same direction or not the same direction as your v initial, can be really helpful. Again, I just don't think we spend enough time in most courses and textbooks talking about this. Where we get to the point that vectors start to seem really obviously useful in 2 dimensions is when students are looking at questions like this one. If an airline pilot is told to fly 123 kilometers in a straight line to get from San Francisco to Sacramento, students understand that that information is not enough information, especially when they look at this map and they see every point on that circle is 123 kilometers from San Francisco, but only one point on that circle is Sacramento. So you have to include a direction. They understand this fairly intuitively just by living in a 3-dimensional space that we grow up in. This question about find the north and east components of the displacement from San Francisco to Sacramento, usually they have a really good understanding of what this is asking them to do, and if they have a memory of taking trigonometry, then they usually don't struggle too much to know how to do this. So the idea that that this question is just asking you how much farther east is Sacramento than San Francisco, and how much farther north is Sacramento than San Francisco. This idea that you can break down that vector into x and y components is visually really familiar to anyone who's done unit circle, even if the term unit circle terrifies them. So we can usually work them through that with a little reminder of what sine, cosine, and tangent are. But conceptually, they do understand it, even if they're not comfortable or familiar with trigonometry. Here's the part I really want to get to for today's brief training video. I'd like you to think about how this example and the next couple of examples are similar to one another, but I'd also really like you to think about how they are different from one another in a way that students would not know to come in and articulate, but in a way that is posing a problem for a lot of students who are learning about vectors. A pedestrian is walking in a 2-dimensional path. They first walk east, then they walk north. When they are done, what is the displacement of the pedestrian from their original location? We compare this to this next slide. We have this rowboat that this person can row the boat, let's say at 3 meters per second, and they direct the boat cross current, and let's say the current is 4 meters per second. And so the actual velocity that they attain is not 3 meters plus 4 meters per second, but this Pythagorean theorem resultant of 5 meters per second, because that's how far they're actually moving each second is 5 meters. That's what's really happening. How is that different from when we start talking about adding together forces? For example, force 1 and force 2 from this question from OpenStax. Force 1 and force 2 add together to give you this force total, or net force, or sum of forces, or whatever you want to call that. Mathematically, this is the exact same as you went a certain number of blocks to the east and then you went a certain number of blocks to the north. So we see that adding these vectors together is done in the exact same way, and we show students that this is done in the exact same way, but something's different. And a lot of students have that difference kicking around in their head, as I said, maybe not in a way that they're able to articulate. We still want to be able to address it. So let's go back to Professor Frank's poll. If individual forces can be said to act on an object, what does the net force act on? And I think the answer, also the object, is a kind of obvious one. That's the answer I think most people would, in this scenario, give back if it weren't a multiple choice. Then you get the object's motion, the mass of the object, or it doesn't act at all. And that last one's a little interesting. What do you mean it doesn't act at all? I spent a lot of time in physics classes adding together forces, individual forces, to get a net force. And the reason that I did that is because the net force connects us into kinematics. We do that through Newton's second law. We take that net force and plug it right into F equals ma to connect our dynamics to our kinematics. How could we say that it doesn't act at all? I think one of the answers to this tweet was an interesting bit of insight that I'd like to share with you. This is a high school teacher in New York State, Frank Noscasi, who says, I think part of the problem is the parallel phrasing we use. There was a whole conversation between all these physics professors and teachers about this today on Twitter. The parallel phrasing we use for real forces, gravitational force, frictional force, normal force, applied force, tension force, we say net force, it sounds like another real force. I think the issue that I would really like us to think about when we are working with students, talking about adding together forces or adding together other vectors, is the idea that we are sometimes adding together vectors that are sequential, and we are sometimes adding together vectors that are simultaneous. And we conceptualize these differently. That's what goes on in our brain when we read a problem, is first this happens and then this happens. We think of that differently from these two things are happening at the same time. And we want students to be able to step outside of that thinking differently about these and recognize that mathematically we treat them the same. So for example, a displacement vector. These vectors are sequential because first you walk to the east, and when you are done walking to the east, now you walk to the north, and when you are done you have a single, as it says here, a single net displacement vector that really does represent your final location's displacement from your initial location. That's an actual displacement, even if it's not the path that you traveled. With forces, this is different. Force vectors, velocity vectors are simultaneous, like with the rowboat there, but I think it's less of an issue. With force vectors, it's much more of an issue that we're adding together simultaneous forces. Gravity is acting while the normal force is acting, while the tension force is acting, and if they're not happening at the same time, we don't add them together and get a net force. So for force vectors in particular, the idea that they add together to create a net force is mathematically true, but it doesn't mean that it creates an actual force in the way that the displacement vectors create an actual displacement. So I think that is exactly Frank Noscasi's point, is that students add together these forces, and mathematically they've created this net force, and they need to not think of the net force as a actual physical force. Two of the places where this comes up that you are familiar with as tutors is this. We know that we sometimes have forces that add together in a single dimension to give us zero net force. And occasionally we run into problems with students adding together forces to get zero net force and then articulating that somehow as there is no force. There's a difference between there's zero net force and no force is acting. Those are different things to say. Mathematically, they're the same in a lot of ways. So we want to be careful with that, and we want students to be careful with that. Of course, the other place where this is famously familiar is when you start talking about objects moving in a circular motion, that horrible centripetal force on the free body diagram. It should never be on a free body diagram. Some force that's on the free body diagram might be described as the centripetal force. We'll get into the dangers and the best practices for centripetal force in a future training video. That's all I wanted to talk about today. Is please, when we're talking about vectors, specifically when you're talking about students adding together vectors that are displacement vectors and then later having to add together vectors that are force vectors, recognize that if a student is struggling with this, it may be helpful to articulate back and forth with them that force vectors that are happening simultaneously add together in a way that is mathematically just like adding together sequential steps of a displacement, even though they are not first this force, then this force. And even though the net force that they create is not a single entity, a single force that we would think of the same way that we do forces like tension, friction, gravity, etc. If you have any questions, as always, please reach out. That's what I'm here for.